once more we touch upon the notion of redundancy, how it comes into play in the context of the polyphase implementation, and how it starts to show ways of dealing with the impairments. So, that is the starting point for our discussion today. So, the multi-carrier transceiver that we are talking about is one that combines M channels, passes it through the channel, splits it back into M channels. Now, this would be a minimal configuration for the multi-carrier transceiver. If this M was greater, was by a factor n which is greater than M, then you would get a transceiver with redundancy. The notations again, at the transmitter we have the synthesis structure, at the receiver we have the analysis structure. The input block, there are M inputs, there are M outputs. So, the redundancy that comes in will introduce some additional signals, but they have to be removed when you actually present the output. So, whatever is happening inside of this block is the parts that we are trying to design, so that we can take care of the impairments that will happen in the channel and also in the block processing. Okay, so a couple of other observations, again just by way of reminder, we have, if you think of each of these as sub channels S0, S1, Sm minus 1, then they could interfere with each other, that would be inter sub channel interference, and then you could have ISI between the elements or the symbols of one sub channel, that would be intra sub channel interference. Both types of interference need to be addressed and need to be resolved. Okay, so if I were to ask you to describe what we have done so far, so this is a good way to capture the information that we have. So, I have a vector that I want to transmit, or a block of data. Okay, so, this is S of n, this is a m cross 1 vector. I would like to pass it through a converter that does time division multiplexing to frequency division multiplexing, that is the synthesis portion, and we would like to introduce redundancy. With redundancy, we have not yet exactly specified, but we know that there will be redundancy that will be brought into the picture. Then this is the signal that passes through the channel. The signal with redundancy passes through the channel. The channel model that we gave yesterday said that there are nu plus 1 taps, C of z is equal to j equal to 0 to nu C subscript j z minus j. Okay, that is the channel model that we have, nu plus 1 taps, it is an ISI channel, new symbols of ISI. We do have noise as part of the system, however, we are not specifically doing anything to suppress it. It will be part on the and I will indicate to you where the noise actually shows up. Then at the receiver, so that's the channel is the channel C of z plus the noise. At the receiver we have to do the reverse operation of splitting the sub channels. So, I call it FDM to TDM, the individual sub channels. Okay. And at this point we also have to do the processing needed to remove the redundancy. Whatever redundancy we have introduced needs to be removed, and leaving us with a vector S hat of n, which is also a m cross 1 vector. Okay, so, basically we have to link these two elements, and we have to demonstrate that. Okay. Now, after going through the polyphase, polyphase decomposition for the analysis, for the synthesis, I believe you will be comfortable if we drew the following figure. Okay, so, I have the polyphase component matrix of the synthesis filters, which are represented by G of z, G of z. There are m inputs going in. Okay. This is S0 of n, S1 of n, m minus 1 of n. There are m inputs. G itself is a matrix. So, this would be m cross 1. G itself is a n cross m, m input, n output. So, this is where the redundancy has come in, but we have not explicitly indicated where the redundancy is coming in. So, we will just show that there are additional branches that are present. We will label them as x sub 0 of n. This would be next one would be x 1 of n. I want to just make sure we get the complete picture. So, we will just draw this one through x 1 of n. Think of this as x m minus 1 of n, and then the last one as x n minus 1 of n. So, basically the redundancy has been inserted. These signals pass through the channel, and through the results from multirate signal processing, we have shown that this can actually be written or drawn in the following way. It can as a pseudo-circulant matrix, of dimension n cross n, n cross n. So, this is CPC of Z, pseudo-circulant matrix. Now, I am ignoring the noise. What comes out of it is the vector r, and just like before, this is an n cross 1 vector. So, let me label them as r 0 of n, r 1 of n. So, somewhere the redundancy is still present, r n minus 1 of n, and then comes the removal of the redundancy. So, here is the matrix which represents the synthesis, the analysis filters, reducing it back down to m signals. So, we again have the trapezoidal form, and this is S of Z. This is a m cross n matrix. The outputs are, there are m outputs, S 0 hat all the way to S m minus 1 hat. So, this is S 0 hat of n, S 1 hat of n, and this is S m minus 1 hat of n. Okay. So, this is the overall framework that we have been able to simplify and obtain, and I am sure that you are comfortable with this. So, you can see that this is the point at which redundancy enters. So, redundancy is inserted, and then on the other side, at the receiver side, redundancy is removed. Okay. So, now how do we design these redundancies? What is it that will give us the best performance? That is what we are, here is the place where we remove the redundancy. Okay. So, basically input output we can relate by means of a, if I took into account G, CPC and S, we now have a input output relationship between S naught through S m minus 1 to S naught hat to S m minus 1 hat. This T of Z is actually an m cross m matrix which we have derived, and each of these elements are obtained using this notation. Okay. And we have interpreted what T of Z should be if you want to eliminate inter-subcarrier, inter-subchannel interference, and if you want to also eliminate intra-subcarrier interference as well. Okay. So, in this process we did not explicitly mention it, but we have used type 2 polyphase decomposition, type 1, this is the synthesis filters. We have used type 1 polyphase component here. Okay. We have used type 1 in the synthesis, type 1 polyphase decomposition, and we have used type 2 polyphase decomposition here. Again, maybe just make a note so that the overall notation, everything sort of will fit in together. Okay. So, how are these elements obtained? You can go through, we have derived these results. So, we will not spend more time on that. Okay, the matrix T of Z, you can interpret it as a polynomial of matrices, and that is what tells us how to get rid of interblock and intra-block, all of those elements. These are the observations that we have. Now, one more comment which is useful at this point. Okay, this is what we had made in yesterday's class. Let me just sort of put it in a box to the right. If the filters, so synthesis filters, there are m of them, f0 of z, f1 of z, fm minus 1 of z. If all of these have length less than or equal to n, okay, this is m is the number of subchannels, n is the redundancy that you are going to introduce, if the filters are of length less than n. Similarly, the same thing applies for the analysis filters which are h0 of z, hm minus 1 of z. If both of these satisfy this condition, that the length less than or equal to n, then this important result G of z, the matrix, and S of z are constant matrices. There is no functions of, because when you do the polyphase decomposition, each of them has got only one entry. So, therefore, you get are constant matrices. Okay, so which means that you can represent it as G, this becomes G, this becomes S. Those are constant matrices which can, again, it will be helpful once we look at it in today's class, but I thought it is a good point to mention to keep in mind. Okay, so the process of simplification involved that we did the polyphase decomposition and also polyphase decomposition of the channel, which is what gave us the pseudo-circulant matrix, and yesterday we did an example of the pseudo-circulant matrix, and we also did some calculations on how to show that if I do zero padding, that the interblock interference is removed. But what I would like to do is revisit that, because there were a few questions after class, maybe a little bit of clarification would be helpful. Okay, now for this matrix, can you write for me what is T naught? Write it in the form, basically I would like to write it in the form T naught plus Z inverse times T1. Okay, what are T naught and T1? Okay, so T naught in this case would be a 6 cross 6 matrix, C naught, C1, C2, C naught, C1, C2, C naught, C1, C2, C naught, C1, C2, then C naught, C1, and then C naught. That would be the T naught matrix. Okay, plus then you would have I do not need to put a plus here, Z inverse times T1. T1 of course would be whatever is left out. So, T1 matrix would have mostly zeros. I will only write the non-zero entries, so you can fill in the others. There would be a C2 here, a C1 here, and a C2 here. That is only the rest of it are all zeros. Okay. So, if I padded with zeros, how many zeros would I have to pad? Basically this is a case where nu plus 1 equal to 3. So, nu would be equal to 2. I would have to pad with 2 zeros. If I padded my input vector with 2 zeros and then processed it through these matrices, notice that I would have to, I can draw a line which separates the last two columns, because they are going to be multiplied by 0 valued entries. And similarly, the T naught and T1 will have that line. Notice that whatever was there in T1 completely got killed, because they were mostly zeros and there were some non-zero elements, but they were killed by the zero padding. And in this case you did have non-zero values, but those also got killed, the last two columns. So, this portion of T naught, the first m rows of T naught was what we referred to as C low. Okay. So, what did we get as the dimensions? You will you can verify that it is an n cross m matrix, which is what we refer to as C low. Okay. So, some observations, if the earlier argument was maybe a little bit confusing, maybe this is one additional way of visualizing it, or maybe even one more way of visualizing it. The R vector we said is the S vector with the zeros appended. Okay. How many zeros? It is a new cross 1 column. So, basically there are new zeros. So, this is a dimension n cross 1 matrix. Okay. Now, basically we have inserted these many zeros, and the equation that we wrote down, a few people were confused. Now, if I take the Z transform of this, so then it becomes R of Z. Now, what exactly am I doing? I am taking R naught, this is R naught, the vector transmitted at time n, the vector transmitted at time 1 with the Z inverse R2, one second I will be with you, and if there is a R minus 1, that will come, R minus 1 will come with a power of Z.
So, we have used the notation x.
Did I use x? X for what? Here, instead of R. Okay, good. I'll change it. Thank you. Okay, so that is correct. That's correct. Okay, R is actually at the output after you get the, okay. So, CPC times X is equal to R, right? That is basically X is the vector going into the pseudo circular matrix. So, the only way I can write this correctly it would be, this would have to be X of Z, this would have to be R of Z. Okay. Let me just explain. Okay. So, R of Z is basically the vectors that are received at each time instant, and if there was a R of minus 1, that would have power of Z. Okay. So, you can visualize that. X of Z, this is nothing but X sub 0, which is obtained by a 0 padding, X sub 1 Z inverse dot dot dot, and of course, if you had x of minus 1, there would be a power of Z. Now, you can multiply the CPC of Z, by the way this is CPC of Z, with the Z transform, this is X of Z, and notice that because of the 0 padding, the effect of the Z inverse terms in CPC actually get cancelled. So, effectively what we will get into the expression when you compare the like powers of Z will be, you will get the following equations. You will get R sub 0, if you were to that is a constant term on the left hand side, will be equal to C low times X 0. No, S 0, because after you have removed the 0 padding. Yes. So, this would be the equation, and at all time instances this is valid, and if you have R sub k, the kth time instant, it is C low times S k. Dimension of C low, as we mentioned, is an n cross m, and we know that n is greater than m because of redundancy. So, this is actually an overdetermined system. Okay. So, now maybe this is a good point to tell you where the noise comes in. Actually, when you process it through this equation will actually will have some noise term present. Okay. So, basically the received signal is S of k passing through the channel plus some corrupted by noise. Now, this is an overdetermined set of system in the presence of with noisy observations. So, the best thing that we can do is the least square solution. Least square solution, the best estimate of Sk will be the least square solution, which is what we wrote down yesterday. the least square solution says that the best estimate for Sk in the presence of uncorrelated Gaussian noise would be Sk equal to the pseudo inverse, Moore-Penrose pseudo inverse. Yesterday we had written a dagger symbol, that is nothing but the Hermitian. So, we will write it down with the Hermitian. C low Hermitian, C low is a constant matrix. So, this is well defined, inversion of that times C low Hermitian times R of n. Okay. So, this is a block by block decision process, there is no interblock interference, and the way we have gotten rid of the interblock interference is primarily because of the 0 insertion. And so, maybe what is worth noting here is that C low corresponds to the first m columns of T naught. Okay, all the other terms got killed because of the 0 padding. Okay, so this is the framework that we derived yesterday. So I hope you are completely comfortable with this representation. So maybe it is good for us to do a block diagram that actually implements this. It may seem a little trivial, but I think this is a potential area where we could avoid any possible confusion. So, I take S naught of n, I upsample by a factor of n, and basically this is the synthesis part where we are combining the signals, where redundancy is going to be introduced. The second channel is S1 of n, and likewise we have m minus 1 channels, S m minus 1 of n upsampled by n. All of these will be combined through a delay chain. Okay, so this is the summing node, all of them are moving in the upward direction, each of these are summing nodes, and all arrows to the right. Okay, this is also going through a delay chain. Okay, now the 0 padding part, very important, because we have only m minus 1 signals, but you are trying to multiplex n ends. So, this is a 0 valued input which you can visualize as being upsampled by n, nothing is happening, but it passes through the delay chain and then gets added to the other, basically the whole process. So, like this there are many branches which are adding only zeros. How many of them are there? That is exactly the amount of zeros that you want to add, new branches, each of them upsampled by n, passing through a delay and getting multiplexed with the rest of the signals. Okay, so this is the representation of the signals there. Now, this combined signal, multiplex signal, which now has the redundancy in the form of 0 padding, passing through the channel C of z. Basically, this will become the pseudo circulant form. Once you take the upsampling by n and you will get the pseudo, and then at the other end, basically the downsampling by n, and what comes out of this, we will call this as R naught of n, passing through an advance operator, downsampling by a factor of n, this is R1 of n, all the way down to the last Z inverse, downsampling by n, this is R n minus 1 of n. Okay, so this is the insertion of the redundancy and what came out of it. So, I throw away the last new entries of R, is that what I should do? How do I get rid of the redundancy? How do I get rid of the redundancy? Not at this stage. I can only remove the redundancy. The reason the redundancy is to help me solve the output. So, basically from here, from this set of outputs, I have to get S hat of n, and that is through the pseudo inverse, and that pseudo inverse actually requires you to have this entire vector. So, do not throw any of these samples away, not yet. The removal or the exploiting of the redundancy and removing it is actually implicit in the pseudo inverse computations that we will show. Okay. So, this is a good point for us to sort of summarize and say, okay, now we have a good handle on what it is that takes the ability to work with zero padded systems and how it all works together, why we are able to get a very clean solution, and we are able to get now the question that we asked yesterday's class was, by the way, we can go back and expand on these in terms of the C of z. Okay. Now, this is the channel model. C of z is equal to n equal to nu C of n z power minus n. It is a symbol space channel model, and the structure of the pseudo circular matrix, again one more time for the full representation we have, we will not expand on this anymore. The pseudo inverse also has been described. This was in as yesterday's class. And the last question that we asked is there any other way by which we could exploit redundancy and also take advantage? And for that we said, yes, there is the processors which will have the cyclic prefix.